apparently I'm very short on time because they told me I have a hard cutoff at 11, so I'm going to keep the acknowledgement very short, so just generic thank you. So what I want to talk today is something like related to what just Lucas illustrated. I'm just going to take some pieces, I'm going to have a little bit of overlap, but what I really want to focus a little bit more is on the quantum gravity side. So I want to try to convince you that quantum information could be a very useful tool to explore quantum gravity in general. In particular, I found this very nice picture that the question that I want to, that really makes very clear what's the question that I want to answer, or try to answer, of course. That's a very difficult question. And this, what is the quantum nature of space-time geometry? And if we can knit space-time geometry directly from quantum information, or quanta. So in particular, I'm going to focus on 3 topics. The first one overlaps a lot of what just Lucas said. So I'm going to try to be short. So I'll try to characterize semi-classical states in quantum gravity in terms of quantum information quantities, in particular entanglement entropy. Since entanglement entropy, we know, is one of the best tools to characterize correlation, as Lucas said, and fluctuation of a quantum state. I want to try to use that to characterize space-time and space-time regions. And then I'm going to focus a little bit more on the question of how you define a subsystem, because while in condensed matter of quantum field theory, the question is kind of more or less understood. In quantum gravity, there's a lot more complications, and I'm trying to show you one in a very simple example and try to argue how you can define a subsystem in such a way that you are compatible with symmetries, gauge symmetries, and in particular, if the entanglement entropy that you want to compute is the one related to observables that are gauge independent, and they're not, for example, gauge dependent, which in principle are not observable, are not measurable in any way, are not accessible. So the third point that I want to touch is the definition of regions and locality, which, again, in condensed matter and quantum field theory, we understood what's a region. It's just a piece of space-time. But in quantum gravity, it's way more tricky to define it. So I'm trying to show you where are the problems and a very tentative solution in a very simple model. So for the first part, I want to come back to the conjecture of the architecture of space-time that Lucas already mentioned, that was formulated by Eugenio like more than 10 years ago, which states that semi-classical states in quantum gravity should belong to the area low corner of the physical Hilbert space. So what's the idea? The idea is that while in condensed matter, for example, you can take, for example, you can start from a thermal state, and you know from what Lucas said that thermal states follow a volume law. So if you compute the entanglement entropy of a thermal state, you will find that the entanglement entropy depends on the number of constituents of the subsystem that you're considering. And then by lowering the energy, you access to states with different properties. For example, you go to area law states and zero law states. But there's no such a clear analogous in quantum gravity of what does it mean to lower the energy. So we don't know how to move in pure quantum gravity. We don't know how to move in the Hilbert space, in the physical Hilbert space. Similarly, in quantum field theory, if you look, for example, at correlation of a test field, you find that the correlation diverges for coincident points. And this is related to the fact that the entanglement entropy of the vacuum for a given region goes like the area of the region times the divergent part that Lucas explained. So instead of using, so the idea is to use the entanglement entropy as a probe for semi-classicality. So use the property that requiring a property of a semi-classical state and using entanglement entropy as a condition on the state and on the region of spacetime. So the idea is to invert the logic. Instead of computing the entanglement entropy of a semi-classical state, we use entanglement entropy to define what's a semi-classical state. And so about that, I want to try to illustrate this hierarchy of states in quantum gravity. So we know that for a spin systems on a lattice, the full Hilbert space factorizes in an Hilbert space corresponding to a certain region containing a certain number of spins and the complement. In a certain way, similar thing is true for quantum gravity. The theory that I'm going to refer to is loop quantum gravity because the one that I work on. And so I made a small mistake and I did not include a full slide to explain what loop quantum gravity is. So let me take 2 minutes. Yes, I have 2 minutes. Yes, I have it, yes. So on trying to explain you what loop quantum gravity is. So instead of giving you a full overview of the theory, let me just give you an overview of what the Hilbert space of loop quantum gravity is. So we can label the Hilbert space of loop quantum gravity with a graph, for example, and a set of spins associated to the links of the graph. And the very nice result of loop quantum gravity is that the Hilbert space is actually a tensor product of Hilbert spaces living at the nodes of this graph. And a very nice way you can interpret these Hilbert spaces is that these are Hilbert spaces associated to quantum polyhedra. So you have a picture of space, which is composed by grains of space. These grains of space are discrete, and they are represented by quantum polyhedra. And we are going to see later what I really mean by a quantum polyhedra. That shares interfaces, so shares areas, and these areas are associated to the spins. Okay? In this particular truncation, so in this particular Hilbert space, you can also think the Hilbert space associated to a certain graph for given spins as a tensor product of, for example, an Hilbert space associated to a region. By region, here I mean a collection of nodes, so a collection of grains of space and the complement. However, there are other technical problems if you really want to give a semi-classical interpretation to these specific states. So in the following, I'm not going to focus to a generic loop quantum gravity states. I'm going to focus on a very simplified toy model, if you want, of quantum geometry, which is the quantum polyhedron. But we're going to see it like in a second. First, allow me to illustrate what's this hierarchy of states that I was talking about. So this is done, of course, in the case of spin system, but you can imagine it if you want also done for the loop quantum gravity Hilbert space, fixed graph and fixed spins. So if you take a random state, as Lucas very well illustrated, what you expect is the entanglement entropy to scale like the volume. So it follows a volume law, and that's a very high temperature state. So if you take, for example, a factorized state, this is like an extremely high energy state, you get a zero law. So you get zero entanglement entropy because the state is factorized. And that's really an element of the basis of the quantum gravity Hilbert space. So to find a state which has good semi-classical properties, you need to find a proper family of states, and there is a proposal that follows the area law, and there is a proposal in loop quantum gravity, which are the Bell network states that were developed by Eugenio and Lucas, and those are the best candidates that we have at the moment that seems to show this property. So those are the states that were constructed to have long-range correlations or prescribed correlations. So let me move to the second question. And the second question is, how do you define a subsystem if your system has symmetries? So in the first part, I'm going to talk about spin systems again. And then in the second part, I'm going to tell you about the quantum polyhedron, and I'm going to show you how you can interpret the quantum polyhedron as some specific spin system. Therefore, I'm going to just mutuate the results from one to the other. So what's the problem? The problem is that if you have a system with some kind of symmetry, the Hilbert space does not factorize trivially in the tensor product between the Hilbert space associated to subsystem and the complement. So let me give you an example. So for example, consider a spin system with n spin 1/2, so the simplest possible qubit system. This system has local observables that are given by the spins of all the nodes of the network. Here I represented a planar network. Like if you can imagine a cubic network, the ideations is not important, so don't focus too much on that. And let's suppose that there's a symmetry. So for example, let's be concrete. Let's suppose that you have a global rotational symmetry. Okay, the global rotational symmetry is generated by the total spin that I'm denoting as J. And this allows us to identify a subsystem in terms of observables or in terms of the algebra of the observables. So what does it mean? So if you have global symmetry, like the rotational symmetry, your observable will in general commute with this symmetry. And therefore, the single spins associated to the single nodes are not observables, and they are not gauge compatible, so they're not accessible. So they define what we call the kinematical local observable, so a k-local observable. So you can define a subsystem in this way, but the problem is that if you define a subsystem in this way, this is like the standard way, by just saying, okay, my subsystem is related to a certain number of spins, and I just take a subsystem, the algebra associated to those spins. The problem with this choice is that these observable mix different symmetry sectors. And in particular, if we have a symmetry, the full Hilbert space decomposes into sectors with associated different representation of the symmetry, and the system is not bipartite anymore. So an alternative that we propose is to use gauge local observable, or G local observable, or group local observable, whatever you want to call it. So you identify the subsystem by specifying the algebra associated to the subsystem, and you define it by taking all the observable associated to a given subsystem. So all the observable constructed from the spins of the subsystem, but that are compatible with the symmetry. So this algebra has the property to commute with the symmetry, and therefore to preserve the sector of the symmetry. So if you use that to define the subsystem, then automatically you guarantee to have a subsystem that is compatible with the global symmetry. How you do that concretely? So I have one slide on that. This is slightly more technical, but what I want to stress is that this kind of construction is fully general. So every time that you have a symmetry in your system, so the system is called, in the jargon, like symmetry resolved, and you have a set of G-local observables. Your Hilbert space associated to a given sector of the symmetry decomposes as a direct sum of tensor products. To do this decomposition, you need to first identify the algebra of observables in the system that are compatible with the symmetry. Then you need to identify the observable in the subsystem. So the observable related to the subsystem that you care about that are compatible with the symmetry. Then you compute the complement, and the complement is defined as the commutant of your algebra of observable. Then you look for an intersection between the algebra of observable related to your system and the commutant, and that's the center of your algebra. And the direct sum that you have in the theorem, so direct sum of the composition, is a direct sum over the spectrum of the observable present in the center. That, say like that, sounds complicated, but in the example that I gave you like right before, if I have a subsystem given by a certain number of spins, the algebra of the subsystem are all the possible gauge invariant contraction that you can do of the spins. And at the end of the story, in the center, you have the total spin of the subsystem. So the sum that you have at the end is just a sum, a direct sum, over the possible spin of the subsystem of a tensor product of Hilbert spaces. Then once you have this structure, then the calculation just follows as usual. So you can define a reduced density matrix, which is a direct sum of density matrix 1 for each sector. So the density matrix is block diagonal. And each density matrix is weighted by a probability. And that's the probability that tells you what's the probability to be in a given sector. And then the entanglement entropy is just the usual von Neumann entanglement entropy of the reduced density matrix. That, if you care about these splits in two parts, let me just mention the names, because in the literature you find names for these quantities. So you get the average of the entropy of a single sector, and this is usually called the configurational entropy. And then you get the entropy associated to the probability distribution. This is usually called number entropy. Yes, 10 minutes, I can do it. Okay, so let me then introduce my simple model of quantum geometry. So instead of looking at the whole full loop quantum gravity, what I want to talk about is just quantum polyhedra. And what is going to end up to be is that these quantum polyhedra are basically just a subsector of your spin system with some zero spin. Let me very quickly illustrate why. So it's a very nice story. I don't have time to go into the details, but I want just to give you an overview. So take a polyhedron. An Euclidean polyhedron are 3 with n faces with given areas. So the areas of the faces is fixed. So the polyhedron is fully defined just in terms of the normals of the polyhedron with the areas associated to those normals. So you take the normals with lengths equal to the area. Minkowski, at the end of the 19th century, proved the theorem that if you take a set of vectors that closes, and that's exactly the properties of the normal of a polyhedron weighted by the area, And there is a one-to-one correspondence between polyhedra and the sector vectors. And then Kapovic and Milson, at the end of the 20th century, they actually proved that this space forms a phase space with dimension 2n minus 3. So that's really a phase space of shapes, because this is a phase space of polyhedra up to global rotations, so they're just identified by their intrinsic shape. So it's a phase space of shapes of polyhedra. That actually what happens is that you can quantize it, being a phase space, and the quantization is what we call quantum polyhedra, but it happens to be exactly the intertwiner space of loop quantum gravity, so the space of grain of space that I was talking about earlier, that defines a state of loop quantum gravity. In addition, the thing that I should mention is that you can define geometric quantities like areas, volumes, angles. And what happens is that all these quantities are operators in the space of the quantum polyhedra. They happen to have discrete spectrum. You can compute all the things that you want. And that's what I think makes the quantum polyhedra a very good testing ground or toy model to do experiments with real quantum geometry. So the thing that I want to stress is that this is a real quantum geometry. It's, of course, toy model one, so it's a two-dimensional one, and it's the simplest concrete example of quantum geometry for the sphere that I know. So in this case, you can also define a subsector, so a subsystem, sorry. So to define a subsystem, you need to define G-local subalgebra, so a set of G-local observables, and this defines your subsystem. So for example, you can take a set of spins. Each spin is associated to one facet, so one face of the polyhedron. And you can define then, you can see then that the whole space of the quantum polyhedra really factorizes into a direct sum of tensor products of Hilbert spaces. And you would like that this Hilbert space that you defined as a G-local subsystem associated to a set of spins, you would like that this describe a patch on the polyhedron. So you would like that it describe a region of this simplified toy model space. Unfortunately, locality in the algebra is not the same thing as requiring locality in space-time. So this is, I have 2 slides left, I should be on time, yes. So this is exactly what I want to stress in this slide. So in the condensed matter quantum field theory, regions are fully characterized in terms of the algebra of observables. So if you pick like a set of spins, this defines a local region in the spin system. If you pick, as Lucas was saying earlier, if you pick like observables that are supporting some region of space-time, you define the region of space-time. You define the subsystem associated to the region of space-time. However, for the quantum polyhedron, if you pick a set of spins, you know nothing about the adjacency of the faces. That's fully encoded in the state, not in the definition of the algebra. So by picking 2 different states, but the same set of spins, the problem is that you could very well describe nearby faces or faraway faces. And therefore, to define a local subsystem of a geometric region is not enough to just have a local subsystem of the algebra of observable, but you need also a good semi-classical state, which is picked on the phase space of the polyhedra, so that would correspond to a geometric polyhedra, where you can really identify a set of adjacent faces. And you need to do it not only by picking on the shape of the polyhedra, but also requiring strong nearby correlation. And this is my last slide. So this is just to connect with the first part, so with the hierarchy of states, and with the talk by Lucas, is that what I want to say is that if you pick a random quantum polyhedra, this is typical. It's exactly the same construction that we have seen before. So you average, for example, over a uniform distribution, you can expect that the average entanglement entropy follow a volume law. Then if you pick a coherent state, so you can pick a quantum polyhedra that is, you can pick, a state in the space of quantum polyhedra that is strongly picked on a shape of a polyhedron by defining a coherent state a la Perelomov, if you want. What you get is that the expectation values of all geometrical quantities are picked on the corresponding classical values. However, the entanglement entropy, if you compute it, you get it that is sub-extensive. And this is related to the fact that there are no correlations between the facets. So how do you improve that? Well, you can improve it by defining the so-called squeezed quantum polyhedron. That is what Eugenio and Lucas did in 2016. So you can define a state of quantum polyhedra. This is like the definition. So you define a matrix that knows about all possible correlation between facets of the quantum polyhedron. And you can compute, in theory, the entanglement entropy for that state, and you're going to find that this follows an area law. So it goes like a square root of n, so it follows the perimeter law, if you want, because here we are in 2 dimensions. And this state is characterized by prescribing both expectation values and correlation through the matrix gamma. Okay, so with this, I want to conclude. Just to summarize. So in quantum gravity, there is the problem of finding good semi-classical states. And the claim is that you can use entanglement entropy as a tool to identify semi-classical state as the corner of the physical Hilbert space following an area law. In the presence of symmetries, it's difficult to define subsystem properly. And if you care about the symmetry and you want to define the subsystem in such a way that is compatible with the symmetry, you can do it by defining the subsystem in terms of the subalgebra of observable compatible with the symmetry. And finally, you can define the notion of region and locality in quantum gravity, or at least in a simplified model of quantum gravity, being the quantum polyhedron, by not only specifying a subsystem which is compatible with the symmetry, which is global rotation, but also by specifying a specific state that has to be semi-classical, therefore you have a notion of adiacency of phases. And with this, I think I'm done.